Rohini College of Engineering and Technology from Department of Civil Engineering. So this is our final year civil engineering 7th semester subject. Our subject title is C8703 Structural Design and Drawing. I am Michael Devadurai, Assistant Professor. So today we have see about the topic is Design a purlin. So Unit 4 Industrial Structures, Design a steel roof truss. So example 1. The design a purlin steel roof truss to suit the following data. So span of the truss is equal to 10 meter. Then type of truss is equal to pan type. Then roof cover is equal to galvanization corrugated sheet. Then materials is a rolled steel angles. Then spacing of roof truss is equal to 4.5 meter. Then wind pressure is equal to 1 kilonewton per meter square. Then draw the elevation of the roof truss and the details of joints with the purlins. Then step number 1, dimensions of the truss. Then central rise is equal to span by 4 is equal to span, we know the span value 10 meter. So 10 by 4 is equal to 2.5 meter. So purlins are provided at intervals of 1.863 meter on the principal rafter. So see the diagram. So our diagram span is the 10 meter. So 10 divided by 3 is equal to 3.33 meter. Then the inclined angle is 5.59. So our purlin intervals is 1.863 meter. So step number 4, wind loads. So F is equal to CPE minus CPI A into APD. This is our formula. So CP is equal to external pressure coefficient and CPI is equal to internal pressure coefficient. Then A is equal to surface area of the structural elements of cladding unit. Then PD is equal to design wind pressure. Then sloping angle theta is equal to 26 degree 34 minutes. Then CP is equal to 0 minus 0.7. So this values are taken from our code book. It's a constant value and CPI is equal to 0.2. The maximum all the problems CPE and CPI is the constants values. Then F is equal to minus 0.7 minus 0.2 into PD. PD is equal to 1. So 0.9 into PD. Then PD is equal to 1 is 0.9 into 1 is equal to F is equal to 0.9 kilonewton per meter square. Then maximum wind load per purlin per meter is equal to 0.9 into 1.863 into cos 26 degree 34 minutes. So 1.5 kilonewton. So step number 2 is dead loads. So self weight of GC sheetings purlins 0.818 meter square. So 0.18 into multiplied by purlin length. Because our purlin length is 1.863 is the distance. So we can multiply it by the purlin length. So 0.335 kilonewton meter. Then self weight of purlin at 0.1 kilonewton per meter is equal to 0.1 kilonewton per meter. So total dead load is equal to 0.435 kilonewton meter. Then step number 3, live loads. So slope of the truss is equal to 26 degree 34 minutes. So live load of the truss is equal to 0.75 minus 10 into 0.1. This is live load into 0.1 and the dead load into 0.1 is equal to 0.02. So is equal to 0.52 kilonewton per meter square. Then live load per purlin per meter is equal to 0.52 into purlin length is 1.836. So multiplied by the purlin length. Then cos theta. Theta is equal to 26 degree 34 minutes. So apply the values 0.87 kilonewton. So step number 5, design of purlin. So for continuous purlin, the maximum factored bending moment and shear force are computed as follow. M is equal to WL square by 10. So this 1.5 is the factor moment, factor load, and 1.3 is the bending moment, W load, and 4.5 is the length. So WL square divided by 10. So this is the moment formula for wind load. So V shear force. So shear force is equal to 1.5 into 1.305 into 4.5 divided by 2 because this is WL by 2. So 1.5 is the factor load, so we can multiply it by that 1.5 factor load. Adopt I is a 100 into 75 into 8 mm having section properties given below. So this section properties is taken from our code book SP1661 ZX, then D is equal to 100 mm, then B is equal to 75 mm, T is equal to 8 mm, then IS 800 2007 class number 3.7. Then check for the section classifications done by computed the ratios. So B by T is equal to B, we know the B is equal to 75 mm and T is equal to 8 mm, so it's less than 9.4. So this section is the plastic section. Okay, section is the considered as a plastic section. Then check for the shear capacity. So AV is equal to 100 into 8 is equal to 800 mm square. Then class number 8.4.1. So AV into Fy W will be V3 into M gamma M0. This formula is in our code book. So you know all the values. You're gonna apply the values. You find out the V value. So 105 kilonewton is greater than 4.4 kilonewton. So hence safe. The shear capacity of the section is very large compared to the applied shear force. So check for the moment capacity. So MT is equal to beta B Z F will be gamma M0. So this is our bending moment formula. So this formula is in our code book IS 800 2000. So beta B is equal to 1. So Z we know that we already find it in our previous step. Into Fy is equal to 250 given in our question. So 1.1 in 10 power 6 is the gamma M0. So MT is equal to 9.95 kilonewton meter. So it's greater than 3.396. So hence safe. So step number 7, load on truss. So dead load. So sloping length of rafter AD is equal to V into 5 square plus 2.5 square. So it's equal to 5.59 meter. So spacing of truss equal to 4.5 meters center to center distance. Then weight of GC sheet of half truss at 0.18 kilonewton per meter square. Then is equal to 4.5 into 5 into 0.18 meters because of half truss, half plane area. So full area is the 10 meter. So half means 5. So 5 into 0.18. So answer is 4.05 kilonewton. Then weight of the purlins, 4 numbers at 0.10 kilonewton per meter. So 4 into 0.1. So sometimes the 5 numbers is 5 into 0.1 into 4.5. Okay, so 1.8 kilonewton. So self weight of roof truss is equal to span by 300 plus 0.05 is the formula. So span is equal to 10 meter. So 10 by 300 plus 0.05 is equal to 0.083 kilonewton per meter square. So weight of half roof truss is equal to, half roof means the full roof is 10 meters, so multiplied by the 5. So 0.083 into 5 into 4.5 is equal to 1.86 kilonewton. So total load on half truss is equal to 4.05 plus 1.8 plus 1.8 is equal to 7.71 kilonewton. So dead load on intermediate minus panel point. So dead load on intermediate means 7.71 divided by 3 is equal to 2.57 kilonewton. Then dead load on end panel is equal to 2.57 divided by 2. Okay. So live loads. So live load on half truss equal to multiplied by 5 is a simple one. So you got 11.7 kilonewton. Then live load on intermediate panel is equal to 11.7 divided by 3 because of 3 points are there, so divided by 3, so 3.9. So live load on end panel point is equal to 3.9 divided by 2 because the end sides are only 2 there, so divided by 2, so 1.95 kilonewton. Then C is the wind load. So maximum wind load acting perpendicular to the sloping surface is equal to 0.9 into 0.9 is the wind load and 4.5 is the load, and 5.59 minus is equal to minus 22.63 kilonewton. Then wind load on intermediate panel point is equal to minus 22.68 by 3 is equal to minus 7.5 kilonewton. So wind load on end panel point is equal to minus 7.5 divided by 2 is equal to 3.75 kilonewton. So step number 8, design of truss members. So members A, B, B, C and C, D. So maximum service load compressive force is equal to 36.17 kilonewton. The maximum factored compressive force is equal to 1.5 into 36.17. So you got the 54.25 kilonewton. So maximum service load tensile force is equal to 22.95 kilonewton. Then maximum factored tensile force is equal to 1.5 into 22.95. So 34.42. So we know that the service load is 22.95. So multiplied by the factor load. We know the factor load is the 1.5 is a constant value. So you can simply know that. So length is the 1.863 meter. Then effective length is the KL into 1.304 meter. Then try two angles. ISA 50 into 50 into 6 mm placed back to back. So area A is equal to 1136 mm square. So minimum radius of gyration Y minimum is equal to 15.1 mm. Then surroundness ratio is equal to KL by RM. So this formula is taken from our code book IS 800 2000 page number 20. Okay, so KL we know that 1.304 meter. So converted to mm 1304 mm divided by 15.1. So it's equal to 86.3. So it's less than 180 and safe. So stress reduction factor into for column buckling classes corresponding to the slenderness ratio. So ratio is the 86.3 and FO is given in our question. So FO is equal to 250 Newton per mm square. Then X equal to 0.56. Then design compressive stress in computed as. So FCD we know the formula. So FO divided by gamma m0. So X is the 0.56 and 250 is the given in our question. So gamma m0 we know that. So gamma m0 is the 1.25. So it will be in our code book IS 800 2007 page number 30. The next our answer FCD is the 112 Newton per mm square. Then design compressive force is given by. So PD is equal to A into FCD. So this formula also in our code book IS 800 2007 page number 35. So A into FCD area we know that 1136 into FCD is the 112. So divided by 1000. We got the answer is the 127 kilonewton. It will be greater than 54.25 kilonewton. So hence safe. So we remember DE. So maximum service load tension is 12.83. So maximum factor load is the 1.5 into 12.83 is equal to 19.24. Because of this is the factor load multiplied by the normal load. So maximum service compression load is 9.57. Then next maximum factored load compressed is equal to 1.5 into 9.57 is equal to 14.35 kilonewton. Then effective length is equal to 3 meter. So try a single angle. So ISA 50 into 50 into 5 mm connected by 6 mm thick gusset plate with the junction with the two bolts of 16 mm at 50 mm. Then cross section area is equal to 479 mm square. Then Y minimum is equal to 15.2 mm. Then use 16 mm dia bolt. Then ANC is equal to 50 minus 18 into 5 is equal to 160 mm square. So AGO is equal to 225 mm square. Then AG is equal to 479 mm square. Then strength governed by the rupture of critical section. So this formula is in our code book IS 800 2007 page number 71. So TDN is equal to 0.9 ANC FY divided by gamma m plus beta A into GO FY divided by gamma m0. So all the values if you can know. So you can apply the values, you got the answer. So 1.4 minus 0.076 50 by 5. So beta is equal to 0.70. So TDN is equal to apply all the values, you get the answer to 83.02 kilonewton. Then strength governed by the yielding of cross section. So TDG. So TDG is equal to AG by FY, the gamma m0 is equal to, we know the AG values and FY is given in our question, the gamma m0 is 1.1. So we got that AG is equal to 108.8 kilonewton. So strength governed by the block shear. So AVG is equal to 5 into 50 plus 50 is equal to 500 mm square. Then AVN is equal to 50 plus 50 minus 1.5 into 18 is equal to 473 mm square. Then ATG is equal to 5 into 25 is equal to 125 mm square. So ATN is equal to 116 mm square. Then the block shear strength is the smaller of the value of TDB1 into TB2 as I computed using. So So the equating given below, the TB1 is equal to, we know the formula, so AVG into Fy divided by V3 gamma M0 plus 0.9 ATFU into gamma M0. So we know the AVG values and Fy values and V3 values also there. So TDB1 is equal to 99.92 kilonewton. So TB2 is equal to, we know that formula, apply the values, then you got the simply answer 109.12 kilonewton. Then hence TDB is equal to 109.12 kilonewton. The design shear strength is the least of the three values computed as A, B, C. So which are 108, 83.02, 109.12. So the design tensile strength of the angle is 83.02. Is greater than 19.24 because compare the three values, take the least value. This is your design tensile strength of angle. So member C, BC and EB member. So service load compression is 6.95, we know that. Then again find out the factor load, simple matter with the 1.5, answer is 10.42, and the service load tensile force is 6.38. So again the multiplied by the factor load, so 6.38 into 1.5 is 9.57. So effective length is KL is equal to 0.7 into 1.6 is equal to 1.2 meter. Then use minimum size angle, ISA 50 into 50 into 5 mm. So area is equal to 479 mm square. Then Y minimum is equal to 9.7 mm. So slenderness ratio lambda is equal to 1120.97 is equal to 115. So the stress reduction factor and corresponding to Fy is equal to 250 mm square and lambda is equal to 115. X equal to 0.39. So design compressed stress is computed as the FZ is equal to, we know the formula, apply the values, get the answers. So 78 Newton per mm square. So design compressive force is given by that. PD is equal to, we know that formula, PD is equal to A into FCD. Our A is in already, we know that, so 79. So FCD is 78, we find out the previous step. So PD answer is 37.36. So this is greater than 10.42. So hence safe. Then D, member EA and EF, the same steps and same format. So maximum service load tension is 32.21. Then factor tension is 1.5 into 32.1748.21 kilonewton. Then maximum service compressive load is 18.84 kilonewton. Then factored compressive load is 28.26 kilonewton. So length of the member is 3.3 meter. So effective length is the KL, so 0.7 into 3.3. So you know the step procedure will be same. So members only it will be changed there. Okay. So try minimum two angles. So I say 50 into 50 into 6 mm connect by the gusset plate, 6 mm thick. So with 6 mm diabole spaced at 50 mm. So area is equal to 2 into 599 is equal to 113.6 mm square. So Y minimum is equal to 15.1 mm. So design strength due to yield of cross section. So TDG is equal to AG Fy by gamma M0. So we know all the values. So just apply the values, you got the answer 258 kilonewton. So design strength governed by the tearing at net section. So TDN is equal to alpha into AU into FU by gamma M0. So assume a single line of 6 mm diameter bolts of two numbers spaced just 50 mm apart, x equal to 0.6. So and AN value is equal to 384 mm square. So TDN is equal to, we know all the formulas, apply the answers is the 75.7 kilonewton. This is greater than 48. So hence safe. So hence the angle section design for the truss can be safely resist the factor loads. Thank you.